Okay, we left off yesterday, I think right about here, right? Okay, we did talk about range because I see from the people in front of me that that is just sort of crossed out. So again, for rational functions, the range question gets a lot more complicated, and we kind of need some tools that we don't have. So this is we revisit this stuff about 2/3 of the way through Calc 1 and like talk about it there. So like just to give you an idea of kind of what we need to be able to do that. So because of that, we're not going to worry about range. The idea is that, this thing, one end is pointing up, one end is pointing down. So I get that part, but in the middle, there's this gap here, right? This space between these things. And to figure out the details on that, we need tools that we don't have yet. So don't worry about range. We'll just kind of get rid of that. But we are talking about rational functions, and because rational functions are fractions, and anytime you see the word rational show up in math context, it means fraction stuff's about to happen. Because they're fractions and because the denominator, six always where I left it, because the denominator is variable, right? X changes, that means the thing in the denominator changes too. It can be zero sometimes. So one of the big things that we're, focused on and need to be aware of is that the denominator might be zero. That affects the domain because the function often has what are called discontinuities, which are places where it doesn't exist, places where to draw it, I would have to lift my pin. We find those by figuring out where the denominator would be zero. So I'm just going to say, watch out for dividing by zero. If an x value would cause us to divide by zero, that means the function's undefined there. That means that value is not in the domain. So we exclude or throw that out. We did that yesterday with this one. Five. Everything's always right where I left it. Setting the denominator equal to zero and solving. In this case, the thing factors, or you can use the quadratic formula. Either way, you get -1 and 6. So at -1 or at 6, we would have 0 in the denominator, right? In other words, if I try to plug those in, I get 2 over 0. Or at 6, I get 9 over 0. In either case, we have something that is undefined. Those are frowny faces. Drew them very small. But we have a thing that's undefined. And more to the point, if we have a thing that's undefined, that means that value can't be in the domain, so we exclude it. The way you exclude a thing with interval notation like this is you say, okay, what's okay then? Anything that's not -1 or 6. Here's the x-axis then. There's -1. There's 6. These are not going to work, but everything else is okay. That means we end up with a domain that's 3 disjoint intervals around those points. So to exclude a single point, we use open intervals, so parentheses, and union around it. That means you can get as close to -1 from either side as you wish, but -1 itself is a problem. This also tells me something else. Anytime we have something that looks kind of like this, of the form, number that's not 0 divided by 0, this means that right next to -1, so, imagine being like here or here, or something nearby -1. There you go. So kind of close to -1. Close to -1, you get something that's almost 2 divided by something that's almost 0. So you're dividing by like a small decimal number. When you divide by a small number, you get back something that is large in return, right? Because that's how math works. That's why the graph, and these often do this, why they start to turn like really sharply, really abruptly to be almost vertical, right? It kind of happens out of nowhere, right? Again, if we think about this like a roller coaster track or something, this is all fine, and then all of a sudden, like, we're very serious about, what's happening, right? So that sharp turn toward the, like, almost vertical, we call that a vertical asymptote. So this has vertical asymptotes at those two values, because the same thing happens over here at 6. And again, it looks something like, number divided by 0. Okay, so I think that catches us up with what we did yesterday. Does everybody feel good-ish about that? Do we have any questions at this point? Okay, I don't know what I'm doing with my hand, sorry. Okay, let's talk about, I don't know, we gotta talk about intercepts, and this is the horizontal asymptote thing. Okay. First question is, does it happen? Horizontal asymptotes are all about end behavior. Asymptotes are lines that sort of frame the graph out, right? So if we ignore what's happening in the middle of the graph and only look at the ends, what happens is we go off the left and right edges of the graph. How would you describe what this end does moving that way? Yeah, I mean, like that, right? Like it's just, flat, basically, right? Level. And this end, same thing. Okay, where are they leveling off? So the fact that it is leveling off means, yeah, there's a horizontal asymptote. Because yes, I can imagine a horizontal line that would fit in there that frames what the graph is doing. Where is it? Looks like it's probably pretty close, if not the x-axis, right? Come on. Here's a zoomed out version. Now we see lots and lots of x values, right? Really far out on the x, really not very far on the y. Where does it look like it's leveling off? I mean, pretty close to the x-axis, right? Okay. Here's how we can sort of confirm that. I need space to write things. Horizontal asymptote, it's in behavior. In behavior for polynomials comes from looking at the leading terms. So we're going to do the same thing here. The only difference is that there's a leading term for the numerator and there's a leading term for the denominator. So we're going to compare what happens with the top and the bottom of this thing. If you want, the idea is basically this, like just look at the top, x plus 3, right? If x is 1,000,000, the difference between 1,000,000 and 1,000,003, I don't really care about that much, right? If you win the lottery and somebody's like, hey, you won $1 million, cool, that's great. If they call you a week later and they're like, hey, we made a mistake, it's actually $1,003, you're like, I don't really care. Like, just keep the $3 for yourself. Have a nice day, right? So far enough out, these two things are the things that do, the heavy lifting. And none of the lower order stuff matters that much. We did the same thing with polynomials to figure out end behavior there. So we take those to the side, x over x squared. And the reason why I want to take those things aside is because it gets some of the noise out of the way, and I can do algebra with this that I can't do with the full thing, right? The original function, I can't reduce or simplify anything there because there aren't any common terms. X over x squared, I can reduce that, right? What's x divided by x squared? Or how do you reduce that? 1 over x, right? It's sort of bottom heavy, right? If we're thinking about the degree, it's 1 copy of x divided by 2 copies of x. Well, you cancel and you get this. If x is really, really big, what does 1 over x start to look more and more like? I'll move the calculator out. What's 1 divided by, I don't know, 1,000? You're like 0.001 or something, right? So the further out we go, the more and more this starts to look like 0. that goes to 0 as x goes to either positive or negative infinity. Which confirms the thing I saw here, where I see the ends, sorry. Okay. Where I see the ends like leveling off and they look like it, they're doing it near the x-axis. I see this, and that confirms for me that, okay, yeah, that is actually what's happening and where it's happening, which means that there's a horizontal asymptote at y equals 0. Because I typed them in, throw those on there. Now, again, those are not the actual function, but they do frame what the function does, kind of nicely and help us see, where it kind of fits in. The idea is that the function itself sort of squeezes in to those asymptotes the further out we go, right? So you see it kind of like tucked into this corner, and then the further out you go, the more and more it starts to resemble those lines. Okay. That leaves the intercepts. How do you find an x-intercept? Let y be 0. If we make y 0, and rewrite the function and put 0 in place of y, we have that, right? Okay, so to find the x-intercept, we need to solve that. Which, might look intimidating, right? Because this thing, A, it's a fraction, B, it's got x's and stuff all over the place, like this looks like a lot. Don't worry about the details. What kind of thing is the thing on the left? It's a fraction, it's division, right? If you divide and you get 0, where did that have to come from? 0 where? Let me say it this way. What's a number divided by 0? Undefined. What's 0 divided by a number? 0, right? Fractions are sharing. If I have 0 cookies, as I do now, okay, and I share them with my 26 or something friends, how much does everyone get? Right. I'm currently sharing my 0 cookies with all of you. So thank you, but fine. Everybody gets nothing, right? Okay. So if this thing, which it looks scarier, is equal to 0, what had, okay, now I'm erasing all kinds of stuff that I don't mean to be. Okay, all right, there we go. We're good now. If that thing is 0, what had to have happened? Where did that have to come from? Right there. It can't be that the denominator is 0. Denominator being 0 tells us other stuff. That tells us where the function doesn't exist, right? Where it's undefined, where the vertical asymptotes are, the stuff we exclude in the domain. It's got to be from the top being 0. So I get to basically ignore that and just look at this. If x plus 3 is 0, then x is -3. So what's the x-intercept? -3. It's a point, so I'm going to write it as a point. It's -3, 0. Just, again, a point on the graph. Okay. What about the y-intercept? Let x be 0. If you plug in 0, what do you get? 3 over 6, 3 over -6. Which reduces. So the y-intercept is 0, -1/2. I know there's stuff all over the place. It's the math. The version of Blackboard's prettier, right? So Look at that if you need to refer back to stuff. Okay, so there's a lot of information to unpack about these things, right? They have lots of features that we need to be able to identify. The domain, the vertical asymptote, those things are kind of tied together. The in behavior, the horizontal asymptote, if there is one, and then the intercepts. Now, the intercept stuff, again, this isn't really anything new. That's how intercepts always work. X-intercept, you let Y be zero. Y-intercept, you let X be zero. That's just what the words mean, right? Asymptotes, if vertical asymptotes are going to be tied into where the thing is discontinuous, which is tied into the domain issue, which all comes back to the fact that dividing by zero is bad, right? So that's the thing to hang on to. You can't divide by zero. All this stuff, or these things come out of that. Horizontal asymptotes, okay, horizontal in behavior, degree, leading terms, right? So we take the leading terms aside and see what they do. And this really is a think about it kind of situation, right? The choices are memorize a bunch of cases or take the leading terms aside, see what they do, and think about what that tells you and how that matches up to a picture of it that you can always grab, of course. Okay, questions about stuff at this point? Okay, so there are lots more problems here. Stuff we want to be able to find: the domain, the intercepts, the asymptotes. Again, don't worry about range, but find the domain, intercepts, and asymptotes. This should feel and look a whole lot like the one right above it. This shouldn't be all that different. So for the sake of, kind of using our time while we're in the same room efficiently, try these first. Sorry, remember my master go to do these first. Find all the stuff, and then we'll talk about it together in a bit here. What happens if you grow? Yeah, it's divided by unit, right? So, the thing that we need to do very little. Or you notice about the domain is this place here where it's right, that the base. So it's not going through an yeah, everything. So. For me, negative force values on the picture goes like that. So that we have this side. And then you think something like that I want. Okay. And that includes zero, because zero is negative. You don't need to like write it down. It's just, it's in there. Right, just, right, it's in there, just like all of you guys do. Yeah. I'm gonna try not to. It's interesting for me because like I always see you guys seated, right? So like everyone's just kind of about the same height. But then sometimes I'll walk up talking and I'm like, oh, or oh.
5 seconds. It's been good to work that. You want that.
Okay, yeah, so take the reading very well. So the meeting turn, you gotta pick out the district. You just want the rate straight, right? Yeah. So it has to be either you want. What that means is not because basically this means something because it is cross balance. So you go to balance and power.
Sorry, we need.
Well, go look at the graph. You got. And if you grab 1/3. That's your plan. Okay, so the fact that, you know, you use 1/3, that doubles
No, 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 I didn't know.
If there's still a negative bottom, that's what you think about the board. I think it would take time. Yeah, right. So you got negative goals, talking about X plus three. Add negative three. This is gonna look like negative 10 divided by 0. Anytime you have something like that, number divided by that's what you get. Yeah, so add negative. Yep. Negative four.
Yeah, so negative four.
That means.
I was looking at my.
Well, at the value, the vertical line is considered which for the graph. It's two is given that. Yeah. Yeah, but that's the vertical line. Yeah. Okay. Okay, so there is one. Yes. If you take the, what is it? The verbal activity is always a place where number of times you're divided by zero. Yes, so that's what I think about it. Yeah. So it's actually but then that reduces. That was. First, what I've noticed is the problems that you have.
What is that?
You just say. What is that? Or only distributed to one, but probably better than one. So if you distribute the two through everybody, you're not really multiplying by two.
Oh, yeah, yes. And that's right.
But think about whether or not you actually do that. What do you think is going to get the top and bottom stretch? already have it factored. So if it's already a factor, can you really even want it? Multiply it out? Guess you're just gonna end up undoing it. Right? They say you somewhere. Okay, so for x-interceptions, you're. Steps to be calculated. So. Really. You've already known what happened about that. You will have to. Okay, let's start with the domain for this one, 2C. What do we need to do? Okay. Okay. How? Okay. There's the graph. Okay, so what we want to see from the graph is that the function's in like two chunks, right? That means the domain's going to be in two chunks too. So there is, one place here where the graph sort of, splits or breaks, right? That's going to correspond to things that we, leave out or exclude from the domain. How do we find where that is though? We set the denominator equal to 0. Okay. We need to solve that. You can distribute the three. You don't have to distribute the 3 because either way, we get -4, right? So what's the domain? Okay. Everything except for -4. Again, not wrong if you distributed the 3, you don't have to. Okay. At x equals -4, what we get is that y would be, or the function would be -4 over 0. Again, that's undefined, but in particular, that sort of thing, number divided by 0, means that there is a vertical asymptote. And that vertical asymptote, again, just to kind of point out, should sort of slot in between that, gap in the intervals for the domain, right? Where the domain, where those intervals are disjoint and we need around a thing. Corresponding to that, we get a discontinuity. That's where that vertical asymptote kind of fits in. Well, the next thing I wrote is horizontal asymptote, so let's do that, I guess. What do we look for? How do we figure out where a horizontal asymptote happens? We can look at the graph and we can say, yes, there is one, right? It does appear to be leveling off. We can't really tell where exactly from this though, right? It looks like, this is a little bit above the x-axis. That's above as well. That looks like it's kind of coming down. This going, so it looks like it's some small positive number, but I can't really, get a good feel for where exactly until we take the leading terms, which are x and 3x. You can take those to the side so that we can do algebra stuff that we can't do with the full thing. X over 3x reduces to 1 over 3. And then the question is, for this, reduced thing that I got from looking at the leading terms, what would that do or how would that behave if x is 100 bajillion, right? This is free from x. There's no x here, right? They reduced out. This is just the number 1 over 3. So it doesn't really care what x value you give it. What that means is that the top and bottom here are about the same size, right? They have the same degree, but in the ratio of 1 to 3. So when I go out really, really far, the bottom is about 3 times the size of the top, but they're kind of, in that same ratio. That means the thing's going to level off and flatten out at 1/3. That's our horizontal asymptote. And that lines up with what we saw from the graph that, hey, it looks like this flattens out. It looks like it's somewhere a little bit above the x-axis. If I throw y equals 1/3 on there, that looks about right. I don't see the thing, sort of being like radically different than that. That looks like it shows me the way for what the ends of the graph do. Everybody okay with that part? Yeah, that's this sort of balancing idea. Okay. All right, intercepts. How do you find x-intercepts? Let y be 0. Always, not just here. Let y be 0. Okay, well, if x over 3 times x plus 4 is 0, that really means that, the numerator must be 0. So what's the x-intercept? And then we get the y-intercept for free. Because it's the same, right? Y-intercept is what happens when x is 0, but if x is 0, we get 0 because we just found that, right? If x is 0, y is 0, and vice versa, so it's both, right? It passes through that one point. Okay. Yeah. No, yeah, there is one, right? It's a point that it goes through at 0, 0. Yeah. Yeah, so this is 0, 0, meaning like the location, right? 0, 0. So yeah, it actually goes through that point. There. Okay. There are questions about that one? Yes. I mean, yes. Okay. Hey, here's another one now. Okay. What's the domain? Nothing easier to understand than a steady drone of several people mumbling at the same time. Okay, how do we figure out the domain? Set that equal to 0, right? And this is a thing that we should be aware of. Sometimes, we see stuff that's factored and we're like, I'm just going to start multiplying stuff out because I know how to do that. I feel like that's in my comfort zone. I'm just going to start expanding stuff, right? Do we actually need to? I mean, usually no, right? I mean, sometimes, but usually we don't. Here, what we're doing is finding zeros of the top and finding zeros of the bottom. And if it's already factored, well, that makes my life a little bit easier. So this gives me -3 and 4 because, again, we've got the factored form. So the domain is everything except -3 and 4. In other words, it's that, and I need to write that down in interval notation. So -infinity up to where? -3 happens first. So we, skip over it, union around, and then from -3 to 4, and then 4 to infinity. Yeah, good. Okay, and at either of those points, if I plug in -3, I get 2 times -2. 20 over 0, which means that there's a vertical asymptote of -3. A similar sort of thing happens at 4. 2 times 5 times 2 over 0, which means that there's also a vertical asymptote at x equals 4. I'm being a little bit, I'm being more thorough about this because than maybe you're thinking to yourself, I need to be. It's possible that at these places that are zeros of the denominator, you also get 0 in the numerator. When that happens, 0 over 0 is called an indeterminate form, like dividing by 0 is still bad, but somehow dividing 0 by 0 doesn't feel as bad, or maybe it's more confusing. I don't know. But what happens here is that you don't get an asymptote, you just get like a removed, like a deleted point from the graph, right? There's just like a hole there. That's not going to come up a lot in stuff that we see, but I got to do the math thing. So this is how you recognize vertical asymptotes. This would mean that you get just a hole in the graph, which again you might not actually see, but that's how it works. Horizontal asymptote. What's the leading term in the numerator? 2x squared, because you got to think about multiplying everything out. You don't need to do it, but you need the first part of it. So 2x squared over x squared. So the degree on top and bottom, 2 over 2, they're the same, right? Which means that the top and bottom are going to basically balance each other out. The x squareds divide out and we get what? 2 over 1 or 2. So the top and bottom are about the same size except in the ratio of 2 to 1 or 2, which means the horizontal asymptote is y equals 2. Yep. The fact that it's balanced means it's going to level off. The fact that it sort of balances out at 2 means it's going to level off at 2. Okay, x-intercepts. Take the whole thing. Set it equal to 0. Yep. And really, we just need to worry about the numerator, which means that either x plus 1 is 0 or x minus 2 is 0, right? So we're leaning really hard on the factor theorem thing. So we get -1 and 2, so the x-intercepts are -1 and 2. And again, I'm just going to write those as points just to help us remember that the points. Okay, and what about the y-intercept? Plug in 0 for x. We get 0 plus 1. Oh, sorry. 0 plus 1, 0 minus 2, 0 plus 3, 0 minus 4. And then do the arithmetic. That's -4 over -12, which reduces to 1/3. So the y-intercept is, again, it's a point. I'm going to write it as a point, 0, 1/3. Okay. So the difficulty here is not in the mechanics of finding this stuff, right? Finding this stuff is easy, provided we know what the things are, right, and where they come from, and like where to look for them, right? So this is a place where, this is kind of like the polynomial graphing stuff, where all of the information that we need is just sort of sitting there, right? Especially when it's already factored like this. The part that we need to be aware of, conscious of, is where all of the information is coming from and how it all kind of fits in together. That's the thing that makes this kind of tricky. So again, the homework for this week is not due until Monday night. So do what you can over the weekend, right? Like approach it as though it's due on Sunday, but don't stress out about things at the last minute or whatever. But do what you can, keep track of things that you want to talk about, or things that you sit down tomorrow and you're not sure about, or I don't know, places where the homework asks something in a different way or whatever. Monday, I'll have some problems for you to work. We'll talk about any questions you have. We'll do some more examples to make sure we got this stuff kind of locked down. Okay. Everybody good? All right. Y'all have a good weekend. I'll see you on Monday.